Hello, everybody. Hello, everybody. I hope you can hear and see me correctly. Welcome to this session. I have the pleasure to chair this section about resilience in the context of climate change. So we will travel in different parts of Europe. So first of all, presentation. I'm Francesco Accatino, researcher from EAAE. And in this session, we are going to travel around Europe. We will go to Sweden with the presentation of Asib Ahmed about heat waves and milk production. Then we go to Italy with Cinzia Zinanti with an income stabilization tool in the context of adverse events. And then Julian Zeilinger with the adaptation of climate change with evidence from Austria. So please write your questions in the chat. I will be able to see them and to pose the question at the end of the presentation. Yeah, so presentation will last 15 minutes with a 5 minutes question each. And now I invite Hasib to give his presentation. Welcome.
Hi. Yeah, thank you so much, Francesco. Let me share my screen. So you can see my screen, right? Sorry. All right. Yeah. So I'll start. So this paper. Just to provide a context, in 2018 there was quite a severe heat wave in Sweden, and we heard that milk production farmers were in distress. So we thought we would see how extreme weather is related to dairy milk productivity, and also look at some of the adaptation strategies and some of the resilience at the cow level, and see what we find on how extreme weather affects Swedish dairy production. So we know that extreme weather and climate change has adverse impacts. Same has been found for dairy productivity and animal health. However, there's still some room for more evidence on sort of strategies like breed level diversification, and to look at dairy production from a resilience lens as well in the Swedish context. So to do this, we broadly have these 4 research objectives, which is to estimate the relationship between temperature and milk production, to estimate the farm level loss due to extreme summer of 2018, and then also understand the impact of heat waves on different dairy breeds that are used within Sweden. And also we want to sort of estimate this trade-off. So this is a bit more animal science, where genetic milk production potential is just sort of so it's sort of an index which comes from cows' parents. So if parents were very high productivity animals, this animal will be judged as a high productivity animal. And we want to see how high versus slightly lower productivity animals sort of fare in when they face negative climate shocks. So we want to estimate this trade-off. To do this, we get our weather data from 2016 to 2019 from the 887 weather stations throughout Sweden. So this weather data is temperature, precipitation, humidity, and we get this monthly milk record data from the Swedish milk and disease recording system. So this data is at the farm level and as well as at the cow level. And we sort of merge this data using the Meteorland package in R to account for spatial correlations between neighboring weather stations. And we define this. So we use sort of 2 or 3 measures throughout the paper, where one is just using sort of this average temperature, average maximum temperature throughout the last 7 days of the milk recording. We also use heat waves, which is defined as sort of this 5 consecutive days where the maximum temperature is above 25 degrees Celsius in the past week. So this is the Swedish meteorological and department's definition of a heat wave in Sweden. So we use these data to sort of answer the above research objectives that I stated. Some of the sort of these summary statistics are average milk per cow is about 26.5. Heat wave is 2%, but this is, 2016 and 2017 had no heat waves, and then 2018 and 19 had some heat waves. So that's why the number seems very low, but actually it's sort of grouped in one year and not in the other years. And BMSCC is the bulk milk somatic cell count, which is basically, think of it as sort of a risk measure and a animal health measure, where a greater number of somatic cell counts is indicative of health problems in cows. And this is at the cow level. We see that most of the breeds that are used are Swedish Holstein and Swedish Red. So to go back to our research objectives, our first research objective really was to understand the relationship between temperature and milk production, and to understand where losses start to happen and where are they the most. So we use generalized additive models. So these models with farm by season fixed effects to control for farm level and sort of this time specific management practices that are unobservable. Milk is milk productivity, and f of j is just the smoothing parameters, where x is the control variables. We are controlling for precipitation, we are controlling for humidity and their square terms. Mu is is farm by season fixed effects, and e is the error term. So what we get out of this is this, where we can see on the left panel this sort of decreasing relationship between the maximum temperature of the past week and milk per cow, so milk productivity. And we see that the losses tend to sort of happen around 14, 15 degrees Celsius. And then after 20 degrees, they are quite pronounced, right? So there's evidence that extreme temperatures, and as number of days of extreme temperatures go up, we will have a problem. The second, the one on the right can be thought of sort of as risk of bad udder health. So somatic cell counts, which are sort of these white blood cells that are now increasing in the milk with the temperature, right? So we have less milk production and increased risk of disease with increased temperatures. One issue with GAMS is that the coefficients are not very interpretable. So when we go to estimate the loss, we go to this temperature bin approach, it shows us a fairly similar sort of graph that yes, as the temperatures are going up, we see more and more losses. But what we want to do with sort of this temperature bin approach is to get these coefficients and multiply them with number of days here, and also with income over feed cost. So income over feed cost is sort of a contribution margin per kg of milk, and also the herd size, right? So what we are estimating is that an average farm is going to get in 2018 it was losing about 700 euros, but the standard deviation is quite large. So obviously, if herd size was larger, you would lose more money. And we think that this is a lower bound of the actual loss, because this loss that we are calculating is only based on uh, this milk production losses, right? And we are not really accounting for any other health issues that happened. So, for example, mastitis can have a positive association with temperature. And once you get this disease, you could have sort of future production can also go down. So we are only looking at milk losses. So in that sense, it's like a lower bound of the loss that we estimate. Next, we want to understand sort of whether some breeds are better off or not. So our sort of this main parameter of interest is this delta M, which is an interaction between the breed of a cow and heat wave. So if delta M was not equal to 0, then that would mean that a certain breed has some advantage in coping with heat waves, right? But our results show that we do not really have any differential impacts on heat waves on different breeds within Sweden. So the most important breeds here are Swedish Red and Swedish Holstein. So we don't see that breed diversification would work very well in the Swedish context. It has worked. There is some literature that suggests that breed diversification works well, but it generally works well in areas where the breeds have very vast differences. So generally in South Asia or Africa, where the local breeds and the imported breeds are very different, then then diversification could work. But in this case, it seems that diversification is not really a strategy that seems to work to blunt climate shocks. And then again, we developed this sort of a difference in difference framework with a continuous variable milk index. So again, as I said, this index is a higher number is indicating that it's a more productive animal. A lower number is indicating that it's not so productive. And what we are interested in is this gamma parameter. So if gamma is less than 0, it would indicate that as the milk productivity potential of a cow increases, it will not perform so well under a heat wave. And so our results sort of suggest this, that a 10% increase in the genetic milk production potential is actually associated with a 27% increase in the impact of heat wave on milk loss. So our sort of this idea that our super animals are not bred to blunt these heat waves, right? So there are implications. Yes, as summers become more intense, or there are more days of summer, we need to be worried about the dairy industry. It will face more losses. Diversification doesn't seem to work, at least with the current state of the animals. And we need to think about these breeding strategies such that the trade-off between milk production potential and climate resilience is minimized. Yeah, so that was my presentation, and I'm open to take questions. Sorry, I can't hear you.
Sorry, I think I was muted.
Francisco, I can't hear you. You're on mute.
Can you hear me?
Yes.
Yeah. So thank you very much.
Sorry,
for
I
this
couldn't see any other screen, so I don't know if I was on time or how did I do.
Yeah, you were perfectly on time. I was thanking you for the very interesting presentation and for being even shorter than 15 minutes.
Okay.
Yeah. So let's wait for some questions from the chat. While we wait for some questions, by the way, there are 89 people in the audience, so quite a high number.
Yes.
So my first question is related to some the use of statistical models. So in the context of climate change, we can go towards unobserved phenomena, weather events or something. So do you think that the calibration, so the models are calibrated in a certain context, do you think they will apply also for future events?
So I'm a little worried about the future simulations or something like that, because we are only taking 4 years of data. So that's why we haven't brought in the future aspect in the paper. But if we had a more longer run, perhaps it would make sense to make some sort of a simulation on 1 degree rise or 2 degree rise in the average temperature. That's my feeling.
Yeah, in any case, your model was quite clear. Above a certain temperature, there is a decrease in milk production.
Yes, yeah.
So there is a question from Susan Fowler.
Mm-hmm.
I read it. As there was not much diversity in the breeds, your conclusion that breed diversity doesn't help. So actually,
so in what we are looking at least with the current breeds that are in use in Sweden, it doesn't seem to help. But obviously, if we sort of figure out which breeds can blunt these shocks and add those to the mix, I'm sure then breed diversity would have a greater impact on sort of ensuring against this climate risk. There's another question: are the results in line with previous similar studies? Yes, they are. There are not many studies that, at least we didn't find many studies that are looking at this sort of trade-off between milk production potential and heat resilience. But the other parts, we are sort of looking that we know that extreme temperature is bad for animal health and animal productivity.
Yeah, you read yourself the question of Simone Severini. Yeah, thank you. So other questions? I don't see other questions. Yeah, indeed. Yeah, about breed diversity can be an added value. Maybe if not, following up the question of Susan Fowler. Maybe breed diversity can bring benefit on other things. Yeah, and so we have another question from Barbara Heinrich. What does your result could mean for warmer countries? And with respect to this, how much do the Swedish breeds differ from those from more southern countries?
So the second part of the question, I unfortunately don't really have an idea on how the breeds differ, but my co-authors are animal scientists, so I'll write this question down, and perhaps it would be good to include this in the policy discussion section. I'm sorry, I can't really make an informed answer about this. But I'm guessing that warmer countries are perhaps using slightly different breeds, and perhaps their cutoff uh, is not at 15 or 20 degrees, or maybe their cutoff is around 25 or 30 degrees. But really, we would have to get this data from the warmer countries and see if they also experience a similar drop, and at what temperature do they experience this drop in milk productivity.
Thank you. Another question from Simone Severini. Are the barns similar within the sample?
So there are some differences in the housing structure of dairy in Sweden, but how does that impact the resilience of cows? I'm not really sure, but again, it's another really good question that I need to think about, and whether or not these sort of housing systems should go in as a control variable or not. That's another question. But we do have sort of these farm fixed effects, so we hope that these differences are averaged out.
Perfect. So I'm sure there can be other questions to be addressed. So you feel free, audience, to contact Hasib. And now we move to the next presentation. Thank you very much, Hasib.
Thanks.
Now it's the turn of Cinzia. Welcome, Cinzia.
Morning, everyone.
Yeah, so you will speak about an income stabilization tool. The floor is yours.
Thank you. I try to share my screen. Okay. Okay. Can you see the full screen? Yes, I think so. Okay. So the climate change enhancing the frequency of the extreme weather events affect farming systems on the backs of farmers and the downstream operators. So this analysis show an example of a risk management strategy into wine cooperative that due to the perceived growing frequency of spring frost is planning to implement a new a sector-specific income stabilization tool. Risk management tools should be aimed at ensuring medium and long run resilience, avoiding relevant and unexpected income losses. What is the income stabilization tool? This is a risk management tool introduced by the European Union in 2013 and then modified by the Omnibus regulation. And it was designed to stabilize the income flows of agricultural farmers. And it is based on a public-private partnership and is managed by a mutual fund that is steered by associated farmers who pay an annual contribution to become eligible for receiving compensation when their income decrease by over the 20% of their average historical level, that in this case was calculated as the Olympic mean referred to the average annual income in the preceding 5 years, excluding the highest and the lowest years. The mutual fund pay until the 70% of the loss by year in case of income drop. But going to the background, when implementing this tool, sometimes there are several elements, pro and cons, because the latter regards, for example, the information asymmetry problems, such as the possible adverse selection and moral hazard, or the difficulty to obtain, so to record income data. But what is positive? Obviously, the mutual fund is directly managed by farmers, and the IST offer an overall income risk coverage for farmers, especially covering for production risk and market risk. Especially in the case of a single cooperative, there is a huge literature on this, and we found some different aspects on the IST in a small region and a single crop, such as the low information asymmetry, because the mandatory participation and the reduced moral hazard. On the other end, the high systemic risk. In this analysis, the focus is to verify the ability of the income stabilization tool to avoid a relevant drop in farm income and to improve the resilience of specialized farming system. Which are the main questions? The first is to what extent the IST will stabilize farm income, and under which condition the IST will be financially viable from the mutual fund point of view, and then how many farmers will be better off with the IST in place. And what's the novelty? So they contain a geographic scale that is a small cooperative of transformation, the specialization of on one single crop, and low information asymmetry, both from cooperative and member side, and an expected utility analysis to study the farmers' well-being with the IST in place. Data focus on wine growers cooperative that is located in the center of Italy, in the province of Viterbo, namely Cantina Sociale di Montefiascone. And with 650 members. Data belong to the period from 2012 until 2017, with a total of 126 observations. But data belong to different kind of sources. Yields, areas, grapes, remuneration, price belong to the cooperative administrative office of the cooperative, of course, and the production cost come from a sample of the farm accountancy data network, defined on the average variable cost recorded in the same period by farmers located in the same province, that is Viterbo, with an area less than 5 hectares. Okay. The income variables is the gross margin obtained by revenues minus variable costs. What about the methodology? To assess the potential impact of the IST, we observed how the mean, the median, and the standard deviation vary with and without the IST in place on the gross margin distribution of farmers. And to assess the financial sustainability of the mutual fund, the compensation cost for the mutual fund have been calculated, a administrative cost. But net compensation cost net of the European Union public support, because we consider that the CAP support the mutual fund with until the 70% of the compensation cost. And the contribution rate making the IST financially viable has been defined observing the cash flow of the mutual fund and the break-even loss ratio level as 0.65 as a fair premium. And okay, the farmers' well-being, the impact on farmers' well-being have been studied comparing the expected utility levels with and without the IST, supposing a negative exponential function with 3 different kind of risk aversion levels, from risk neutral to high risk averse. Assumption for the study regards farmers are rational agents, and the time series can represent past and future income conditions. What's the results? So the first result, if you look the graph, you note as the total income of the sampled farms as a rather constant trend. Except for the year 2017, in which to a sudden frost, there was a high production losses that with a significant impact on the income, on the final income, roughly minus 17% with respect of the average income of the period. But the first result is that while keeping the average income constant or stable, the IST strongly reduced the variability of farmers' income. Of course, looking at this graph that show the cumulative distribution of IST net compensation, the trend of compensation undergoes a peak in 2017, if you look at the blue one line, as evident from this graph, specifically the almost 67% of the farms resulted compensated in that years, against an average of the 30% of the whole sample in the whole period. Okay, this is the second result on the financial sustainability of the mutual fund, where we found a premium rate, so contribution rate of on average 5% to the sustainability of the mutual fund. That is the minimum contribution rate that the mutual fund have to be asked to the farmers to be sustainable. And the time series analyzed show also the a positive cash flow for the whole period, excluded for the year 2012 and 2017, where the mutual fund pay a big amount of compensation in that years. However, the cumulated cash flow evolution demonstrate that large precautionary funds to avoid bankruptcy may not be required. Obviously, if the conditions of 2017 had occurred at the time of the mutual fund establishment, so the first year, the fund would inevitably have had to resort to borrowing. And then going to see the balance with the better off of farmers. If you can see this graph, the minimum contribution rate is supposed to 5%. We found a willingness to participate of 80% from the farmer's point of view, even despite a medium high risk aversion. If you look at the bottom of the graph, concluding we found that the IST will stabilize farm income and increase its average level. The IST will be financially viable for the mutual fund, considering the minimum contribution rate at 5%, and the mutual fund will be able to ask all farmers to participate under a multi-annual contract basis, reducing the problem of adverse selection. And the small-scale geographical concentration and specialization do not prevent the sustainability of the mutual fund, because, however, the extent of systemic risk, nature of the risk, is not large enough. And many farmers will be better off with the IST. So we found more than 80% of the sample. They are farmers able to adopt the IST, so with a large willingness to participate between members of the cooperative. Okay. Thank you. I can hear you, Francesco. Can you unmute your microphone?
I think, yes, always the same mistake I do. Thank you very much, Cinzia, for your very nice presentation.
Thank you.
We have a question from Mauro Vigani.
Mm-hmm.
So the question is, would the IST compensate in case of reduction of farmer earnings? Your calculation of a gross margin does not account for such drop in earning due to risk occurring. So shouldn't you adjust the gross margin for the dropped income?
Yes, I think I can, but if you want to include my collaborators, my authors that would like to try to answer also for, thanks, Mauro.
Yes, it's not very clear to me that the question raised by Mauro. It's not clear to me. Maybe we want to discuss the issues later, Mauro.
So
I mean, I don't know if Cinzia wants to show the formula of the gross margin that's given by the revenue minus the specific crop costs.
Yes, I can.
And this is very much in line of what is decided at the national level as income indicator.
Okay.
yeah.
Try to share. No, okay.
Yeah, you can share the slide quickly, and then we go to the next presentation.
But maybe I don't know if Mauro wants to. Okay. Okay.
Yeah.
Okay. Thank you, Mauro. Other questions?
Maybe you can discuss later this.
Okay.
Yeah, I have a very, very quick question in case. So your work depends on many parameters. Do you do some sensitivity analysis about that? That can affect, because parameters can affect your conclusions.
Yes, we found the results of the sensitivity analysis are not in this presentation, but we considered that probably the problem was the yield losses. So we found this kind of if you look at the graph here. So the same trend we found for the yield in the world period. So the year 2017 found a decrease in losses that have a strong impact on the final income. So we found this is in a sensitivity analysis, this is the variables that have the biggest impact on the gross margin or income trend.
Okay, thank you very much, Cinzia.
Thank you.
And thank you. We give now the floor to Julian.
Oh,
Welcome.
okay. I think we're quite busy on time, so I'll start right away.
Yep.
I think you can see it. Okay, hello everybody. My name is Julian Zeilinger, and I'm presenting the work on climate change adaptation evidence from Austrian farms, which was prepared together with my colleagues Andreas Niedermeyer, Abdul Kudos, and Jochen Kantelhardt. And agriculture is an economic sector which is highly influenced by climate change, and therefore adaptation to climate change is a key goal. And many member states within the EU are applying specific measures to mitigate its impacts. And in order to derive unbiased long-run effects, the possibility of adaptation has thus to be accounted when assessing those impacts. And an extensively used method is the Ricardian approach, which considers those long-term adaptations, but also imposes the strict assumption of full or perfect adaptation. And still, adaptation is a quite complex process, which requires multiple factors such as information, awareness, and resources. And in consequence, there is upcoming evidence that farms are not responding sufficiently to climate change, and therefore perfect adaptation does not prevail. And therefore, this study accounts for those potential limitations of climate change adaptation at the farm level, and further derives the extent of adaptation. Quickly to the methods. We depart with the economics model from the Ricardian methods, where farmers are assumed to have adjusted their production practices over the long run to the climate they are facing, and therefore maximize profits. The expected long-run profits V bar are thus a function only of the exogenous variables climate W bar and Xi, which are additional controls such as soil or subsidies. In this graphic, the long-run relationship between climate and profits is depicted. And if we consider the Ricardian approach, the farms have to be perfectly adjusted to the climate they're facing, and thus no higher profits can be achieved. Still, as I've already pointed out, recent literature has identified various limitations to climate change adaptation that can hamper the process and lead to a slowed down adaptation. And therefore, we do not assume that farms are able to perfectly adapt to the climate they're facing, but we rather expect them to be lagging behind due to missing information, resources, and/or technologies. Consequently, if farms are not able to perfectly adjust, the observed long-run relationship, which is the black line, would not represent the highest attainable long-run profits anymore, and the optimum and thus perfect adaptation would lie above it. But with the Ricardian method, the optimum cannot be identified unless the farms are able to achieve it, and even then we would not know it because we only observe one long run. Therefore, to identify the climate change adaptation of farms, we follow Moore and Lobel and rely on a second measure, which is weather, while the long-run profits are depending on climate. The short-run profits within a year also depend on the weather variation. And therefore, we can distinguish between two responses, which is the long-run response that denotes how profits will change if farms are able to partially or fully adapt to changing climate. And the short-run response denotes how farm profits will change with different weather conditions given a certain climate, where farms are not able to implement long-run adjustments because it is not feasible within one growing season. Okay, just checking the time. I think we have no more time. Okay, so we have the long run and the short run response, and using both simultaneously allows us to identify the climate change adaptation of farms, which is expected in two cases. The first one is the assumption of Ricardian methods, perfect adaptation, which prevails if unexpected weather deviations of weather from climate always lead to diminishing profits. And the second case would be imperfect adaptation, where unexpected short-run weather deviation could also result in higher profits than those attainable in the long run. To visualize this, on this graphic you can see, on this slide you can see a graphical representation of both cases. The solid line represents the long-run response to climate, while the dashed line represents the short-run response to the weather given a certain climate, which is indicated by the dots. And on the left, you can see perfect adaptation as at the climate W0, the long-run profits yield V bar 0, and short-run profits would lie below at V0. And consequently, the current long-run adaptation to climate W0 is profit maximizing. On the contrary, on the left side, you can see imperfect adaptation as at the climate W0, the farms face long-term profits V bar 0, sorry, which are below the highest attainable profits observed V0. And therefore, the current long-run adaptation of the farm to climate W0 does not yield highest attainable profits anymore. So how do we estimate this relationship? We extend the framework of Moore and Lobel and estimate an econometric model using panel data, which relies on both cross-sectional variation in climate and interannual variation in weather. Our dependent variable is farm profits per hectare, which depicts the value of agricultural activity. And the meteorological variables are depicted by W bar, yes, sorry, and D, which contain a vector of growing season temperature and rainfall. The long-term climate is W bar, which represents a farm-specific 20-year moving average, and D represents the yearly weather deviation, which are differences between annual weather and climate. And as you might have noticed, the weather deviations are further split up so that it captures impacts from warmer and cooler weather separately, and thus helps to identify adaptation. Further, we add interaction terms between weather deviation and climate to allow the short-run responses to vary with climate. And finally, to control for observed and unobserved heterogeneity, X represents an additional control, which is subsidies per hectare, and alpha and V denote time and farm fixed effects, respectively. So we're short on time, so we'll skip the data. We use an unbalanced panel data of Austrian farms in arable regions. So much to say. And moving on to the results, we can here see the long-run response to climate, which is the solid line. And we estimate we find an inverted U shape, which means that profits are increasing up to a certain point and then decrease again, and estimate a maximum farm profits at the growing season climate of 16 degrees Celsius, which largely corresponds to previous studies within Europe. regarding the assessment of perfect adaptation, we add the short-run response curve, which is the dashed line. And we find that in the case of cooler temperature than expected, the short-run response lies above the long-run response, denoting higher profits. And this is fully in line with our expectation of a short-run optimum above the long-run response, indicating lacking adjustments and thus contradicting the assumption of perfect adaptation. Finally, the interaction terms between weather deviations and climates allow us to assess how the short-run responses vary with climate. And in the graphic, you can see 3 exemplary short-run responses and the red curve, which represents the optima of all estimated short-run responses. And you can clearly see that the potential profit gains are much higher with increasing climate, and possible explanation is for us that agriculture has to be found particularly vulnerable to heat, and therefore imperfect adaptation might lead to higher impacts in warmer climates. So to quickly sum up, we find that farms do not seem to be perfectly adjusted to the climate they are facing, which suggests that the very common assumption of perfect adaptation does not hold, at least in our study. And further, we find potential gains of additional adaptation to increase substantively with increasing temperature, which stresses the need for development and implementation of effective adaptation measures as climate change is ongoing. Okay, thank you for your attention.
So thank you very much, Julian, and sorry for the very tight timing. Thanks for sticking to it.
Rushing through it, but I think the most important parts are covered. So
sorry for that.
No
so
problem.
my question I have is about the multidimensionality of adaptability. So I'm not sure if I interpret correctly the model, but I think adaptability has multiple dimensions, and if you adapt in one dimension, it can be maybe not perfectly adapted in another dimension. So do you take into account multidimensionality of adaptability?
Yes, I understand what you mean, that farms can be adapted differently, but as the study region in Austria is quite small and also homogeneous, and farms are quite homogeneously have homogeneously technical standards and also resources and information in a small country like Austria. We assume that the adaptation is similar between the farms and only account for same adaptability.
Okay.
But if I understand correctly, you mean that farms can differently adapt and therefore have different standards of adaptation.
Yeah.
Yes, you can extend this framework to work with some exogenous index or something that would measure the adaptability of farms.
Okay, thank you. So we have another question, but I don't know if we need to start the next session. By the way, it's in room A in a few minutes. No time. So sorry. But well, you can interact with Simone Severini, which demands about the time required
Yes.
for adaptation and compliments for your paper. So unfortunately, time is really against us, and we can move to the plenary session in room A. Thank you very much for all your participation. We were 90 people here, and see you in the plenary. 92. Yeah.